Hello Hacksters, and welcome to Embedded Programming 101. My name is Michael Hall. I'm a developer evangelist at ARM, and today I'm going to walk you through the very basics of embedded programming. This session assumes that you have some programming background, an application developer of some kind, and you're interested in doing more embedded programming, but you don't know where to start. So this is going to take you from having no knowledge necessary to ready to start working on your own embedded programming projects or being able to just better follow along with the demos that you're seeing here at the event. So to start out with, what do we mean by embedded programming? Well, the good news is that there's no fundamental difference between embedded programming and traditional programming. A lot of the things that you're already used to, a lot of the data structures, the flow control, that's all going to be exactly the same. The biggest differences that you're going to find are that embedded programming generally has fewer resources available to you. So not nearly as powerful of a CPU, a lot less memory, and little or no on-device storage. So your programming, the way you do it is going to have to change. You're going to have to consider those resource limitations rather. You're also going to have your software sitting a lot closer to the hardware. Traditional environment, if you're doing desktop or mobile or web programming, there's a lot of abstraction between your application code and the device it's running on. With embedded, you're much further down. You're going to be talking much closer to the hardware itself. So you're going to be working at that lower level. Also, usually embedded programming only runs one application at a time. There's not going to be multiple apps going on. There's not a way to switch between apps. You load up the device and it starts up and it starts your one application, and that's pretty much it. But other than that, it's going to be very familiar to you if you have a programming background already. So what you're used to is this traditional computing stack. Usually you've got the hardware at the bottom layer. On top of that sits the firmware, which is somewhere between hardware and software. This is a set of software that knows about the hardware and how to talk to the hardware, and also provides a standard interface for the software that sits on top of that to be able to facilitate that communication back and forth between them. Usually the software that sits on top of that is going to be comprised of the operating system kernel, so the Linux kernel that knows how to talk through the firmware to the hardware. That's also where your device drivers and stuff sit. Again, those all talk through the firmware hardware. Then you've got the rest of your operating system and one or more apps. Usually a bunch of apps, right? Desktop and mobile, you've got apps all over the place, and ways for the user to launch them and close them and switch back and forth between them. Running on ARM, an ARM device like a laptop or a server or even a mobile phone is much the same. Usually you've got a Cortex-A or Cortex-M processor. So Cortex-A is for applications. That's what's running in like mobile phones. That's the kind of thing that you'll find on laptops or on servers. XM is for microcontrollers, so that's stuff that's smaller than a laptop, usually low power, running on battery, something like that. On top of that is ARM System Ready, which is about the equivalent of a firm of APIs that sit on top of ARM hardware for the software on top of it to be able to communicate through without having to know exactly where it's running on. And on top of that, you've got your traditional operating system stack with the kernel, the operating system files, and your applications. So if you're running like a Raspberry Pi, you've got Raspbian on there, you've got the desktop and everything. This is the kind of stack that you're used to running on ARM. Again, it's very similar to what you would run on a traditional x86 desktop. But with embedded, you don't have that operating system. So that means you have no Windows, you have no Mac OS, you don't even have Linux available to you. What you do have in the embedded world is you have an RTOS, a real-time operating system, and that kind of combines the operating system and the firmware side of things. So it sits directly on top of the hardware. Now the RTOS needs to know exactly what hardware it's running on. Part of your configuration and your installation process is going to be telling that RTOS the exact kind of device it's running on so it knows how to access the hardware on that. And then that RTOS provides an interface layer to your application, which sits on top of that. Now, the application and the RTOS will both be bundled together when they go onto your hardware. It's not like a traditional desktop where you would install Ubuntu and then install an app. you cram the app and the RTOS together, and then you stick that whole package onto the device. There are several real-time operating systems that you can choose from, especially for ARM devices. You can use the open source, which is part of the Linux Foundation. You can use free RTOS. ARM has ARM OS, which is an open source embedded OS that you can use. Or if you're using like an ESP32, you can use the Espressif RTOS, which they provide for their devices. The big things that an RTOS does is it provides a framework for your application. So you as an app, you don't have to write an operating system yourself. You don't have to know how to interact directly with the hardware. It's going to provide that abstraction layer for you that you would get in a traditional kind of operating system environment. Again, they include device-specific code. If you go and you download Ubuntu Desktop, it doesn't have anything specific to like a motherboard on there. There's device drivers that you can get, but the basic thing you're downloading is really agnostic to the hardware that it's going to run on. Whereas with an RTOS, you have to have specific board packages. So you can say, I'm running this specifically on like an ESP32 or a Raspberry Pi Pico or something like that. And then again, that code, the RTOS code, the device-specific code, and your application code then all get built into a single binary package that gets run to the device. Some big differences you're going to find from a traditional software development stack. First of all, you're not going to have files or file system. And there's a little asterisk on here because that's not always true. But at the default level, the basic level, you're not going to have files and file systems. Sometimes the RTOS can make that available if that's something you want. That usually includes a lot more overhead, though, that you may not necessarily need and you're not going to want on the low resources of the device you're going to work with. You're also not going to have very common things like standard in and standard out. You know, when you're writing an application, even a basic command line application, you have access to these on a desktop. You're not going to have that on an embedded device. What you might have, though, is a serial console, which will let you have an input and output stream that can then communicate to something else over a serial connection like USB. Most of what you're going to be working with are things like pins and voltages. So you're going to be directly interacting with the physical world instead of a virtual software-defined world. And the data that you're going to be dealing with is going to be either analog values of voltages coming on those pins or digital signals that are just ones or zeros on or off on those pins. If you have more complex data or a more complex peripheral that you want to use, there are interfaces like PCI on a computer would be. So you've got SPI and I2C for that kind of complex data. The I2C is good for integrated circuits, like if you've got a analog to digital converter that you're using, or if you have, say, maybe an LCD screen, that's going to use the SPI interface to let you send graphics data to the screen. So stuff that's more complex than just ones and zeros or analog values, you've got those interfaces in an embedded environment that you can use. If you are coming from a desktop or a mobile app development environment, some of the big things you're going to notice right away is that you have no windows or activities or whatever that high level kind of class is for your application. It's not going to be there. Your code's going to start out in the main program of your C, or if you're using Python, whatever the main function is for Python. So you're not going to have windows. You're not going to have cards or activities or anything like that. You're not going to have mouse or touch events. Again, the asterisks, because some RTOSs will provide that for you. If you have like a capacitive touch screen connected to your SPI interface on your board, you can get touch events. That's all much higher level. When you're first getting started and you've got a basic board and some basic setup, though, you're not going to have that. So you're not going to think about input events. You're not even going to have keyboard input events. Again, you can have that serial connection, but for starters, just assume you're not going to be able to type anything in to your device. You're not going to have multi-threading capabilities or multi-processing abilities. Again, it's possible with the RTOS, with the right board, you can do this. By default, though, it's all going to be single-threaded, single process. The RTOS is going to start your application is going to run, and it's the only thing that's going to be running. You're also not going to have a GUI library, so you can't say, I want a button here or a frame here or display a picture here. There are GUI libraries that you can use combined with things like an LCD screen that you can attach that will provide that abstraction layer for you. But again, not built in, not the default. If you're coming from a web development background, first of all, you're not going to have a client or server. That whole model that you're used to where you have a server and a client connects to it, not going to be there. Once again, the asterisk, because some of these boards do have networking capabilities like Wi-Fi, and you can technically run a web server off of those. It's actually remarkably easy to do, but I digress. A little more complicated than we're going to get into for this workshop. So since you have no client and server, you're also not going to have that request and response kind of workflow. So you're not going to get a request from a user. You're not going to be able to send a response back to them the way you would if you were writing like a .NET or a Python server application. No front end, no back end. You're not even going to have a browser. So forget about JavaScript frameworks altogether. Most of what you know as a web application developer not going to exist in an embedded world other than the basics like flow control, right? So this is what your stack is going to look like. I'm going to look at the ARM stack right now, but it's going to be similar for any other kind of embedded device that you're going to have, whether it's a ESP or a RISC-V or something like that. So you're going to have the hardware device. In this case, we're going to use a Cortex-M for microcontroller. That's what we're going to be using a little bit later in the workshop. And on top of that, you're going to have some kind of RTOS, like the Embed OS that ARM provides. And on top of that RTOS, you're going to run your application code, which for Embed OS is going to be a C application. You could also use Zephyr here, in which case Zephyr is your RTOS, and your C application is going to interact with their APIs instead of the Embed OS APIs. You can actually run Python code on a lot of these devices. In that case, you're going to use MicroPython, which acts as the firmware. So MicroPython has that device-specific code that, so it knows how to control the device. It's going to bring up a Python environment for your Python application to run in, and then that's all it's going to run. So MicroPython is not just an implementation of Python. It's its own RTOS and everything built into that. And it supports a wide range of hardware, including a bunch of the Cortex-M boards. What we're going to be looking at today, though, is using the Arduino Core as our RTOS and writing an Arduino application, which they call a sketch, that's going to run on top of that, and all of that running on top of a Cortex-M board. Some of the things that we get from the Arduino Core, first of all, it provides a bunch of different board supports for a whole range of Arduino devices, including devices that use different chips. For ARM boards specifically, it's going to actually use that ARM Embed OS as the underlying layer. So Embed OS knows how to talk to the ARM hardware already. Arduino Core is building a layer on top of that to provide that Arduino environment on top of Embed OS running on ARM hardware. Now, two of the big things that you're going to interact with Arduino programming are the processing API and the wiring API. And these are both things that Arduino has borrowed from other existing projects. The big things that we're going to get from that processing API is the setup function. And this is going to run just one time when your board starts up. What's actually happening when you compile your Arduino application is it's going to create a C main function like any other C program would have. And that main function is going to call setup one time at the start. Once setup completes, that main function is just going to keep calling the loop function. And it's going to do this just forever. So what you define in your loop function is what's going to keep happening on your device over and over and over again. You can slow that down when you need to by calling the delay function. And that just tells that loop to stop for a given amount of time, and then it'll pick right back up again. Now, from the wiring API, you've got all of the functions that let you interact with the pins on your device. So it's pin mode tells the underlying system whether or not a pin is going to be used for reading data or for writing data. You can only do one at a time per GPIO pin, so you have to specify what you're going to do. It also provides constants for that function. So if you're going to be reading data from it, you're going to tell it that by using that input constant. And if you're going to be writing data to it, you're going to use that output constant. It also provides you functions for reading and writing those pins. So for reading and writing digital values from them. In our demo, we're going to be using the GPIO pins, which are just digital. They're not analog. So you only have two options on those. Either you have a 1 or a 0. And those are represented by these high and low constants, which correspond effectively to having a high voltage on that pin or having a low voltage on that pin. And there's thresholds that the device is going to use to decide whether a certain value is high or low. It also provides this serial class, which lets you read and write to a serial connection, like over a USB connection. I mentioned before that you had that as an option on some boards. The serial class that we get from the Arduino Core is what's going to let us do that. So things like serial.println is what we're going to use to send output logging data back to our development computer. All right, so now we're going to get into actually assembling our hardware. So I'm going to switch my camera over so you can see me as I do this. Here we go. All right, here you can see my my little development board. This is a Raspberry Pi Pico. This is a relatively new device by the Raspberry Pi Foundation, and it is using their, I think it's their first custom designed chip. This is the RP2040 that uses an ARM Cortex-M core in it. And the kit that I got came with this really nice sticker sheet here, so I can put my stickers here on my breadboard. Makes it easier to tell what pins that I'm working with. Now, you may be saying, wait a minute, I thought we were working with Arduino. And we are. We're going to be working with the Arduino IDE and the Arduino Core software. Fortunately, Arduino makes their own. Move that out of the way. Arduino makes a Arduino Nano that uses that same RP2040 CPU that the Raspberry Pi Foundation designed. So that's this one right here. And you can see same one right there. So because they're using the same chips, the Arduino Core library for the Arduino Nano RP2040 will work just as well on the Raspberry Pi Pico. So we're going to take advantage of that here. Now, I'm going to switch back so you can see slides as well. Let's see. All right, so I've got my board here connected to a breadboard. If you've never used a breadboard before, they're super, super useful when you're doing any kind of electronics prototyping because you don't have to solder anything to connect your devices together. The way they work is these middle rows here all have connections that go kind of perpendicular. You can see in the screen here, they're all connected that way. And then you've got these rails on the side, which are all connected kind of parallel to the board. Those are handy if you are going to be connecting a lot of devices together. You can provide one input voltage and one ground pin to those rails and then connect everything up to that as well. For this workshop, though, we're just going to use these kind of parallel lines to connect things up. And you can see the pins line up to the numbers on my sticker there. So all of the holes between them are going to be connected. I can use any of them that I want to connect to the right pin on my Raspberry Pi. We are also going to be using a couple of sensors. The first one is going to be this PIR sensor. It's a passive infrared sensor. This is used in most motion detection applications because it's really cheap, it's really effective. Basically, it's going to see infrared photons coming off of a moving body, and it's going to trigger based on that. There are some controls here that you can use to adjust the sensitivity and the timing of that. We're just going to leave ours turned way down for this demo because we're not building an actual prototype device. We're also going to be using a little piezoelectric speaker. These are real simple, real cheap. You give it a voltage and it makes a beeping sound. So those are the two devices that we're going to be using here. And we're going to wire it all up with our Raspberry Pi. So let's get started doing that. First thing we're going to want to do is make sure that our Pi is firmly connected to our board. We don't want there to be any gaps here. We want it pressed down all the way. Do be careful pressing it down. You don't want to bend any of those pins. Just apply a nice constant pressure across the whole board if you can. You can kind of do a little bit more on one side than the other. Just kind of be gentle with it, but make sure that it's stuck in there nice and firmly. So this is what the pins on our Raspberry Pi look like. There are different things that you can do with each of those pins, such as the I2C or the SPI interface that I talked about earlier. But for this demo, we're just going to be using the GPIO pins. So we're going to be using the green strips that you see here on the slide. Those also correspond to the numbers that I have here on the sticker. The kit that I have came with a nice little card that's got the same graphic on it. So that's super helpful. All right, so the first thing we're going to do is we're going to connect up our passive infrared sensor. So move that out of the way for a second. I'm going to take my my three little pins here. So I've got these jumper cables, have different ends on them. So these ends, the male ends, are going to go into the breadboard, and these are going to plug into the sensor. So I'm going to plug these three in here. Easier said than done. There we go. All right, so the piezo or the passive infrared sensor has three pins. It's got a voltage input pin, it's got a ground pin, and then in the middle there, it's got the data pin. And what's going to happen is when it detects data, that middle pin is going to have a high voltage value or a 1. And when it's not detecting motion, that's going to have a ground voltage or a 0 value. So we got those three plugged in. I'm going to bring our Pi back in here. And we're going to connect this. First of all, we're going to connect our ground line, which I am using black here, to our ground pin right here. You can see. Let me zoom in a little bit. There. So we're going to connect this here to our ground pin. The next thing we're going to do is we're going to take our voltage input pin, which I used the white one, and we're going to connect it to this 3V3 pin here. So that's 3 volts that is coming off of the Raspberry Pi. It's going to get that from plugging into our USB connection, or if you had a battery, it would get it from there. And then the last thing that we're going to do is we're going to connect our data pin over here to GPIO number 28. Now, it doesn't really matter specifically which GPIO pin you connect this to. You're just going to need to know which one it's connected to when you go to write your Arduino sketch. Now we're going to kind of do the same thing with our PIR sensor. Oh, let me get that out here and find the wires that I'm going to use for it. All right, so once again, I'm going to use going to use white for my positive voltage and black for my ground. So I'm not sure if you can tell here, but there's a little plus sign on the top of this that tells you where to connect the positive line to. So I will do that. And then I'm going to connect the ground line to the other side. And now back here, I'm once again going to connect the ground wire to a ground pin. The Raspberry Pi has multiple ground pins, so that makes it a little bit easier on us. So I'm going to plug it into this ground pin right here. And then we're going to connect our voltage in to one of our GPIO pins. I'm going to connect it over to pin number 19 because it's right close by. Again, it doesn't matter which one you use here as long as you remember which one it is when it comes time to write your software. So that's what I've got. I've got my passive infrared sensor connected to voltage in to run it, ground pin, and then a data pin so it can send a signal back to our Pi. And then I've got our speaker connected to ground and then to one of our GPIO data pins so that we can selectively turn on and off our speaker. All right, now it's time to write our software. So we'll get back to just the slides and we'll go over that. All right, you can either follow along as I go through the lines of code individually, typing them in yourself in the Arduino IDE, or you can go just grab the repo that I have here on GitHub. That's got the full code there, and you can just load that up into the Arduino IDE. So if you clone that, just navigate to wherever you clone that to and open up that pir_sensor.ino file. The .ino file is an Arduino sketch file, which is essentially just a C application file. In your Arduino IDE, you're going to have to tell it what kind of board you have, because again, it's going to have to compile board-specific code into your binary and upload that onto your device. So if you go up there to the Tools menu and go down to Board, you will find the Arduino Mbed OS RP2040 boards. You do have to install the board support package for this. You can do that under the Board Manager. So if you see there under the Board menu, at the top it says Board Manager. If you don't already have that RP2040 on there, go to the Board Manager and it will find that from the Arduino site and install that for you. So choose the Raspberry Pi Pico from that board selection there. The next thing you're going to need to do is tell it which port on your computer you're connecting your Raspberry Pi to. If you're on a Mac, it's going to be something like /dev/cu dot something or other. It should say Raspberry Pi Pico there in parentheses. If you're on Windows, this path is going to be something like COM3, COM4, something like that. If you don't see it on there, even after you've got your device plugged into a USB port on your computer, you may have to click that upload button at the top of your Arduino IDE. That's the one that's got the little right-hand facing arrow on it. Sometimes these boards come without anything on them to set up the serial connection. So hitting that upload button will put that initial Arduino Core firmware, essentially, the RTOS, onto the board so that it can show up as a serial device for you. I don't actually remember what these Raspberry Pi Picos came with, because the first thing I did was went and flashed an Arduino script onto them. All right, now let's go look at the code itself. At the very top of the code file, you're going to see that we're setting 3 variables, and these are going to hold the numbers of the GPIO pins that we connected up earlier. Again, these are just variables, so it doesn't really matter what the name is. It's just there so that we can refer to it by name further in the program instead of by number, because we are going to be using it a lot. That means if you have connected your sensor or your speaker up to a different pin than the ones that I used in the demo here, all you have to do is change these variables to point to the right pin number. So once again, we connected the motion pin up to GPIO number 28. We connected the buzzer pin to GPIO number 19. And here you see we also have this LED pin connected to GPIO 25. And you didn't see me connect an LED onto this because we're using the built-in LED. The Raspberry Pi Pico has one that's built into the board, and it is connected up to GPIO number 25. So all we have to do is use that, and we don't actually have to put an LED onto our board. All right, the next thing we're going to do is define some variables that are going to be used by our program. The motion state is going to hold the current state of the PIR sensor. So every time that we go and check it, that's where we're going to store that value. Long term, though, we're going to store that into this val function. Oh, sorry, I got that the other way around. Motion state is what we're going to use to hold long-term values, and val is what we're going to use every time we iterate through it. And what that's going to do, having these 2 separate variables, is it's going to let us see if that state has changed. So if it was in a low state before and it's in a high state now, we know that something's changed, motion has been detected, and that's when we want to act on something. We're also going to use this counter variable. This is just to show you that it is going to maintain state across each loop. So it's going to start counting from 1 every time it detects motion, 1 up until you unplug the device. So those are the variables that we're going to use for our application. There are some helper functions that I've written just to kind of make the main chunk of code a little bit easier to read. The do beep function is going to kind of beep our speaker. It's going to do that twice. It's going to have a short beep and a slightly longer beep. And to do that, we're going to use that digital write function that we got from the wiring API. We're going to tell it which buzzer pin we have the buzzer connected to, so that's the pin it's going to write to, and we're going to tell it to write a high value, or a 1 or a high voltage. And what that's going to do is it's basically going to turn on our speaker for us. So as long as there's current running through the speaker, it's going to make noise. So we're going to let it do that for 1/10 of a second. So the delay function takes microseconds. So 100 microseconds is about 1/10 of a second. After that, we're going to turn it off by setting the output to low on that pin. We're going to wait another 1/10 of a second. We're going to turn it back on again, this time for 2/10 of a second, before finally turning it off. So that's going to give us our little beep sequence whenever we want it. The next helper function is for turning on the LED. And similarly, it's going to use that digital write function. It's going to this time use the LED pin, that built-in LED that I mentioned earlier. And it's going to give it a high value to turn that on. And likewise, the LED off function is going to do that in reverse. It's going to write a low value to that pin to turn the LED off. Now, I mentioned the setup function earlier. This is what the processing API uses. It's going to be called once as soon as you power on your board. These boards don't have an on-off switch, so it's really based on whether or not it's powered on, and you can power it on by plugging in USB cord to it, and it'll draw power from the USB. Or if you have a battery or a solar panel or some other source of electricity, you can connect that up to the voltage input pins on the board and power it that way. However you power it, as soon as it does power on, it's going to call this setup function. And here we're going to do our initial setup so that the board knows what pins to use and what it's going to use them for. It's also going to set up that serial connection. So you can see that first line, that serial.begin. That's going to set up the serial console that you can use to communicate back and forth between your board and your computer. Then it's going to set the pin mode for the motion detector to be input, so that now the board knows it's going to be reading data from that pin, not writing data out to it. It's going to do the same thing, only the other way around for the buzzer pin. It's going to set that to be an output. And as well for the LED pin, it's going to set that to be an output. And by default, we're going to turn that LED on. So for our uses, if the LED is on, that means the device is ready to go. It'll turn off when it detects motion and turn back on again when it's ready to detect. And the last thing we're going to do in this setup is we're just going to write a line to our serial output saying that our device is ready to begin detecting motion. So that's it. That's all the setup that we need to do. Like I said, the Arduino Core does a lot of other stuff in the background that you don't need to worry about. The next main function that we're going to write is our loop function. This is the one that's just going to get called over and over and over again as long as the device is powered on. So here's where the meat of our application is going to be. This is where the bulk of what you're going to be doing is going to be written. So the first thing we're going to do every single loop, we're going to read the value of that motion pin. And we do that with the digital read function and pass it the pin number variable. And we're going to save the value of that into that just val variable that we created earlier. The next thing we're going to do is we're going to check and see if it is currently high or low. Again, means that motion's detected. Low means that motion is not being detected. So this is where our logic branching really starts to set in. If it's got a high value, the next thing we're going to need to know is whether or not this is a new high value or if we've been in that state for a while. So to do that, we're going to check that motion state variable. Again, that's the one that holds the previous iteration's value. So if it was low in the previous iteration of the loop and it's high now, we're going to write motion detected out to our serial output. Then we're going to call the LED off function to turn off our onboard LED. We're going to call our do beep function to make our little speaker beep. Then we're going to increment our counter variable. Again, we started at 0, so the first time it detects motion, it's going to bump that up to 1. And then we're going to write out what our current count is, again, to that USB serial connection. And then here, importantly, we're going to set that motion state variable to high, so that the next iteration of our loop, that motion state will say that it's already high. And if it's high again, we know that it's not a new motion detection event. Now, if the previous state was not low, meaning, again, it was high at the previous state, we know that we've already done the beep, we've already changed our LED. So now we just need to wait for that sensor to what I call cool off. So the motion detection sensor will hold that positive value for a short amount of time. So we don't want to beep constantly after it's detected motion. We want to wait for it to go back to its ground state, not detecting motion before we trigger another beep event. So if we detect a high value immediately followed by a high value, we're just going to wait, and we're going to wait 5 seconds for that. However, if we detect a low value from the motion detector, meaning that it's not saying that it's detecting motion, this time we're going to check that motion state again. And if it was high previously, that means that we've come down from detecting motion to not detecting motion, and we can go back into our ready state. So once again, we're going to save that motion state for the next by saying that that motion state was low. We're going to turn the LED back on, indicating that the board's ready to detect motion again. And we're going to print out to the serial console that we are ready for detection. Now, at the end of every loop, I've got this half-second delay, because otherwise it's just going to hammer your board constantly. This code doesn't take very long to run, and we don't need it to detect at a super high frequency. Like half a second is more than enough for motion detection. This will certainly save you wear on your CPU. More importantly, it's going to save you battery power if you are running it off of a battery. So it's not just running 100 times a second. It's only running twice a second, kind of at most. All right, now we get to upload that to our board. With your board connected to USB serial, you can go to that sketch menu and click upload, or again, you can click the upload button on the IDE. That's a little right-hand facing button. And that will put that onto your board and go ahead and start. Again, it'll start the setup function first, run that one time, and then it'll start calling the loop function. And you can watch the output of that, because we are going to connect it to USB, and we have the serial class setting up that connection and writing data out to it. You can pull up the serial monitor on the Arduino IDE and watch that come in. So now I'm going to flip back around so that you can see my board. All right. And I've got my USB connection here. We'll go ahead and plug that in. Make sure I'm getting a good connection here. All right, there we go. So our little LED turned on, indicating that we are in a state where we can start detecting motion. And now if I kind of move my motion sensor here, we should see that in a second turn off. Let's see. There we go. So you can't really hear the beep. My speaker I've kind of blown out, so it just kind of makes a real soft ticking sound, which is good because the beep is actually fairly annoying. But now you can see it working there. And if I switch over. All right, so this is my serial monitor connected to my Arduino IDE. And you can see that I'm getting that output that we were printing out to it, where it'll say, it's ready to detect. It'll detect motion. It'll tell you what the current value of the counter is. There it goes. Let you know when it's waiting to cool off. Actually, I can share both of these so you can see it in action. There you go. So the lights turn off. Waiting, and the lights back on. It's ready to detect again. All right, let's move that. Go back to I'm going to unplug this so that I don't keep hearing that ticking sound. Let's pull our slides back up here. All right, so that's the end of our presentation. Go back to our presentation. So like I said, this is a very rough intro. We're not doing anything specific, but if you've never done embedded programming before, this is a really great way for you to get started. If you've followed along with your own Raspberry Pi Pico device, which is super cheap, if you don't have one, you can go buy one. I think they're like $15, $20 or something like that. And these two devices, the infrared sensor and the speaker, also super cheap, just a few cents a piece for them. And then these jumper wires. You can actually get a kit. This is the kit that I use. Let's see if I can zoom out here and you can see the whole thing. So I got this, oh, it's upside down. This starter kit that comes with it comes with a breadboard, it comes with a Raspberry Pi Pico, it comes with all of the jumper wires and most of the sensors that you could ever use. It did not, however, come with the detector. I had to buy that separately. But all told, $50 for the kit and the sensors, pretty good deal. So if you've got that and you've followed along, now you have a embedded device. You've been able to write application code for it. You've built that application code into the Arduino Core RTOS, and you've flashed the whole thing onto the device. So now you can start following along with some of the other examples you've seen. And every time you see how to do that, it's going to be a similar process. You're going to have application code sitting on some type of RTOS, and then you're going to have tools that let you build the application, the RTOS, and the board-specific code together into a single binary and upload that onto your development device. I hope this has been a fun and educational session for everybody, and I look forward to seeing what you go out and start building on your own. Thank you, everyone. Well, I hope everybody enjoyed that presentation. We do have a few minutes for questions, and there have been a couple already, so I'm just going to jump right in and start answering those. So we had somebody ask in the Zoom Q&A, which Pico in the board manager in Arduino IDE did you pick? So I picked I think it was the Embed OS RP2040. Let me see if I can screen share real quick. There we go. So this is the one I use. It's the Arduino Embed OS RP2040 boards. This was actually designed for the Arduino RP2040, which I do have right here. Let's see if that's not going to focus on that because there's no light. But tiny little Arduino board has the same chip as the Raspberry Pi Pico. So that same Arduino Core package will work for this or for the Raspberry Pi. I went with the Raspberry Pi for this demo just because it's cheap and widely available. This one's a little bit more expensive because it comes with things like the Wi-Fi and Bluetooth chip on there. Which kind of brings us to our second question, which was asked over in the Discord by Audie. Part of it's a little bit more complex for me. I've never designed a PCB, so I don't really have any advice on that end of things. But if your current setup has got a little board that's doing the sensor collection and then making a serial connection to a Raspberry Pi for Wi-Fi, that to me feels kind of heavyweight. The Raspberry Pi is going to use a lot more battery if you're running out of battery. I just threw my board. So if you're making your own PCB, I would suggest figuring out a way to put a Wi-Fi module on there. Both the Arduino and there's a variation of the Pico that both come with a Wi-Fi and Bluetooth module on them. You might be able to just put one of those on your board and use that and put it all just in one package. That'll save you complexity. It'll save you power usage. It'll also give you control over that. So if you only need to upload data once an hour or once a day, you can turn that Wi-Fi off and back on again just when you need it. So you can make things a lot more power efficient that way. But again, I've never made a PCB, so I don't know what the process is. I don't know how to wire up a Wi-Fi module to these chips, but it sounds like maybe you do, or at least you're already on that track. So I would recommend going that route. And please share what you do, because I'm interested now in how that would work.